Here is what we're getting at. Remember, the electrons are out here. Do they really live like this? No, they're found in regions of probability called orbitals. We can collapse that all into the idea of an electron cloud. Red particles are protons, and blue particles are neutrons in a densely packed region called the nucleus. This would be carbon-12 because we could count 6 protons, 6 red particles, and 6 blue particles. Here's carbon-13, and here's carbon-14 with 8 neutrons. So that's what we're getting at. We are using the idea of isotopes to talk about the number of particles in the nucleus of an atom. So far, you guys should be able to use the periodic table to think about the atomic number. You should know about the chemical symbol in the name. You should know the atomic mass is the average mass of all the naturally occurring isotopes of that element. And you should know what an isotope is and how to use the mass number to determine the number of neutrons in an isotope. All right, let's get more specific now about electrons. The periodic table, it turns out, is not only organized according to atomic number of protons in the element, it's also organized according to where the electrons are found around the nucleus of an atom. This gets quite complicated, so I'm going to make it very simple. You're going to learn more about this whenever you take chemistry. But it turns out that even though we can only know about the regions of probability of where electrons are in an atom, that's called the orbitals, we do know they have to be in specific regions that we call energy levels. So electrons are arranged in energy levels located around the nucleus. And the periodic table can actually help us determine how many electrons are in the different energy levels. So we're going to make what is known as energy level diagrams. We're going to represent every atom like this. The nucleus in the middle, and then even though this is not accurate, it is the simplest way of thinking about it, and it will help us for now. We're going to use rings around the atom to represent energy levels. So this first ring represents the first energy level, and I'm going to place dots in here to represent electrons. So maybe I'm looking at an atom that has 2 electrons in the first energy level. Then the second ring. The first energy level, by the way, can only hold 2 electrons. All the rings after that, we're going to show as holding up to 8. So I'm going to show 8 electrons in the second energy level, like this, trying to make it kind of symmetrical. This would be what I'm going to call an energy level diagram of an atom. The nucleus in the middle, and then here's a region called the first energy level. Here's a region called the second energy level. There are 2 electrons in the first energy level, 8 electrons in the second energy level, so on and so forth. Well, just by looking at the periodic table, we actually notice a pattern of how the elements are arranged and organized. Let's fill out these diagrams for the first 20 elements very quickly. Hydrogen, helium have been done. So remember, going down, these are known as periods, period 1, 2, 3, 4, periods of the periodic table. And then going down this way, these are called groups. So group 1, group 2. A piece of this table has been taken out for simplicity. So it's groups 3 through 12, I believe, have been taken out. So this would be group 13, group 14, group 18. Here are the noble gases in group 18. So I'm only going to do this for the first 20 elements. You will only have to do this for the first 20 elements. After calcium, you get into a region of the periodic table known as the transition metals. Let me just pull that up and show you. So after calcium is scandium, the first transition metal. This is the section of the table that was removed in the other diagram. What's happening with the electrons here is a little bit more complicated, so I'm never going to have you diagram or model or think about the electrons here, just for the first 20 elements, hydrogen through calcium. So lithium has 2 electrons in the first energy level. Remember, I told you the first energy level can only hold 2. Anything after that we're going to show as holding up to 8. So lithium has 2 electrons in the first energy level, 1 electron in the second. Does that make sense? Yeah, its atomic number is 3. What does that represent? That's the number of protons, and it's the number of electrons, right? Because those are equal. So 2 electrons in the first energy level, 1 in the second. That's great. Let's model beryllium. Beryllium has an atomic number of 4, so I know I must model 4 electrons. Well, 2 of them are going to be in the first energy level, and 2 of them are going to be in the second energy level. Really doesn't matter where you put them. Just like that. Pretty simple, right? Boron has a total of 5, so 2 in the first energy level, and then 1, 2, 3 in the second energy level. Carbon is going to have 2 in the first, 1, 2, 3, 4 in the second, so on and so forth. So I've filled out the entire second period. You're just adding an electron each time. So beryllium has 2 in the second energy level. Boron has 3 in the second energy level. Carbon has 4. 1, 2, 3, 4 in the second energy level. Nitrogen has 5. Oxygen 6. Fluorine 7. Finally, neon has 8 in the second energy level. Now remember, how many electrons, for the purposes of this class, does the second energy level hold? It holds 8. The first energy level can hold 2, the second can hold 8, and every energy level after that can also hold 8. So now when I come here to do the third period, I'm in the third energy level. Sodium has 1 electron in the third energy level. Magnesium, I'm going to have 2 electrons in the third energy level, right? 2 electrons in the first energy level. I know that the second energy level is already full. It has 8. There's the second energy level, so that's 10 electrons. I need 12. So 11, 12. It has 1 more than sodium. Okay, so I've gone ahead and filled out the third and the fourth period. There are 2 incredibly important patterns that you must notice. Perhaps you've noticed one of them. Have you noticed a pattern involving the period number that the element is in? Yes, the period number is the energy level that is getting filled up as you go along. So I'm going across the first period. I'm putting electrons in the first energy level. It can hold 2. There's only 2 elements in the first energy level. The second period, I'm putting electrons in the second energy level. Lithium has 1 in the second energy level. Beryllium has 2 in the second energy level. I'm adding 1 each time. So I'm filling up the second energy level until neon I've put 8 in the second energy level. So I come down here to sodium in the third period. What do I need? I need the third energy level because the second energy level can only hold 8. So now I'm putting 1 in the third, 2 in the third, 3 in the third, over. Chlorine has 7 electrons in the third energy level. Argon has 8 electrons in the third energy level. Finally down here, the fourth period, I need 4 energy levels, and potassium has 1 electron in the fourth energy level. Calcium has 2 electrons in the fourth energy level. Again, every time I go down a period, I need a new energy level because the previous energy level has gotten filled up. Argon has 8 electrons in the third ring, in the third energy level. It can only hold 8, so I'm coming down here. I'm adding a fourth energy level. Potassium has 1 electron in the fourth energy level. So there's the first biggest pattern: is that the period number tells you the energy level that's being filled up, the outermost energy level. The period number corresponds to the outermost energy level of the element. There's another pattern that has to do with the groups. Look down group 1. Do you notice a pattern from hydrogen to lithium to sodium to potassium? Hydrogen has 1 electron in the first energy level. Lithium has 1 electron in the second energy level. Sodium has 1 electron in the third energy level. Potassium has 1 electron in the fourth energy level. Yeah, so the group number, how far over we are in the period, will tell you how many electrons that element has in the outermost energy level. We call those valence electrons, and they're incredibly important. Valence electrons are the number of electrons in the outermost energy level of an element. And the pattern is that all group 1 elements have 1 valence electron. Hydrogen has 1 electron in the first energy level. Lithium has 1 electron in its outermost second energy level. Sodium is the first element in the third period, so it has 1 electron in its third energy level, 1 valence electron. Potassium is the first element in the fourth period, so it has 1 electron, 1 valence electron in its outermost energy level, the fourth energy level. Beryllium is the second element in its period. It has 2 electrons in the second energy level, so it has 2 valence electrons. Boron has 3. Carbon has 4, so on and so forth. Any element in the same group has the same number of valence electrons. Beryllium has 2, magnesium has 2, calcium has 2. Calcium has 2 in the 4th energy level. Magnesium has 2 valence electrons in the 3rd energy level. Beryllium has 2 outermost valence electrons in its outermost energy level too. Boron and aluminum have 3. Carbon and silicon have 4. Nitrogen and phosphorus have 5. Oxygen and sulfur have 6. Helium and chlorine have 7. Helium only has 2, so this is one break in the trend. Helium only has 2 because the 2nd energy level is only capable of holding 2 electrons, but then anything below that, those are all going to have 8 valence electrons. Neon has 8 in the 2nd energy level. Argon has 8 in the 3rd energy level, so on and so forth. Those are called valence electrons. So once again, valence electrons are the electrons found in the outermost energy level of an atom. The number of valence electrons determines many of the chemical properties of the element. So going back to our big periodic table, the period number tells you how many energy levels that element utilizes. The group number tells you how many electrons the element has in that outermost energy level. Now, we are going to ignore the transition metals because I think I told you their electrons are complicated. So this pattern picks back up over here in group 13. Well, do you notice a pattern? Do you remember how many valence electrons boron had, or how many aluminum had, how many carbon had, how many silicon had? Boron and aluminum had 3 valence electrons, carbon and silicon had 4. Do you notice something? Yeah, so for these we want to look at the last digit of the group number. Group 13, group 14, the 5, the 6, the 7, and the 8. So for this part of the periodic table over here, and for this part right here, we have a name for all of these elements put together, by the way. We call them the main group elements. For the main group elements, the number of valence electrons is equal to the last digit of the group number, group 1 and group 2. All of these have 1 valence electron. What does that mean again? It means they have 1 electron in the outermost energy level, which corresponds to the period number once again. So potassium will have 1 electron in its outermost 4th energy level. Calcium will have 2 electrons in its outermost in its outermost 4th energy level. Over here to the other main group elements, 3, boron, aluminum, gallium, all of these have 3 valence electrons. Boron has 3 electrons in its outermost 2nd energy level. Carbon has 4 valence electrons in its outermost 2nd energy level. Silicon has 4 valence electrons in its outermost 3rd energy level. And why do we care about valence electrons? Because once again, the number of valence electrons greatly determines the chemical properties of the element. That is why everything that has 1 valence electron is classified as the same type of element, because they all behave similarly. Alkali metals all have 1 valence electron. These guys, the alkaline earth metals, all have 2 valence electrons. The halogens over here, how many valence electrons do they all have? They're in group 17. They all have 7 valence electrons. The noble gases, right here, with the exception of hydrogen, with the exception of helium. Helium only has 2. Every other noble gas has 8. That's why these groups of elements are similar to each other, because they have the same number of valence electrons, and the valence electrons, by and large, determine the chemical properties of the element.